Test the claim that the mean GPA of night students is larger than 2.9 at the 0.025 significance level. So the first thing to do is figure out what information has been given. So we're told to test the claim that the mean GPA for night students is larger than 2.9 at the 0.025 significance level. So our significance level is our alpha, and that is 0.025. We also have the, oh, can't do that. Okay, we also have in this introduction down here, based on sample of 25 people, so we have N 25. The sample mean GPA was 2.95, so that's your X bar, 2.95, and with a standard deviation of 0.03. Now that's talking about the sample, so that is not the sigma, that is the sample standard deviation, not the population standard deviation. So we don't know sigma. Sigma is unknown. So being that sigma is unknown, we're going to end up doing a t-test. And we need to figure out our hypotheses in order to know which one of these to pick. All right, so first of all, we are doing a claim about a mean, so it would be the Greek letter mu, would be our parameter symbol. And the value that was in the claim was the population mean mu. We have the claim that it's larger than 2.9, so we're going to go on the null assumption that it's equal to 2.9. So the claim is that it's greater than 2.9. The assumption, the default assumption, is that it's equal, and since there's no equality in the claim, it becomes the alternative hypothesis, which makes this a right-tailed test. So we're doing a right-tailed t-test, and we want to pick the mu with the greater than symbol. And I don't like that they're using a less than or equal symbol there, but try not to be OCD about it. All right, now the left tail, two-tail, right tail, we'll pick right. And now we will calculate the test statistic. So the test statistic is taking our sample statistic and turning it into a standardized score. Since we're doing a t-test, it'll be a t-score. And since our sample mean 2.95 is larger than the claimed population mean of 2.9, it's larger, so it's going to have a positive t-score. And I don't normally jump right to doing the test statistic. I just was led that way because of the problem. But I'm going to go ahead and do my critical region first because I already have some information that I can use here. So my significance level of 0.025 is going to go right here. And the area to the left, since it is a right-tailed test, I'm going to do 1 minus that. That's the area on the right. And that way my critical value, which is a t-score under the t distribution, is going to be positive since it's on the right-tailed test. And I'm going to use norm.inverse with my left area. Mean of, well, we don't do mean and standard deviation for t distribution. Oh, I put norm.inverse, didn't I? I meant to put t.inverse with my left area, and degrees of freedom is always n minus 1. So in this case, 25 minus 1 would be 24. And the p-value is going to come next. So now I have my critical value, and now I'll do my test statistic, and then I'll find my p-value. All right, so my test statistic is just like doing a z-score for central limit theorem, except it's a t-score. because we're using the sample standard deviation. So what we're going to do is we're going to take our sample mean x bar and subtract the claimed population mean 2.9 because we're doing this under the assumption that the null hypothesis is true. And then we're going to divide that by the standard error. Well, what's the standard error? The standard error is your S divided by the square root of n. And I'm just going to put that in parentheses also. Or if you don't want to mess with a bunch of parentheses, you can figure out your standard error in here by just doing S divided by the square root of n. And that way, when you go to calculate your test statistic, then you can just do x bar minus the claimed mean divided by the standard error. So now we have our test statistic. That is a crazy high. I wonder if there's a mistake. Nope, that was it. That's super high. Remember that by the empirical rule, we expect about 95% to fall within 2 standard deviations. The empirical rule doesn't exactly apply to the test statistic. I meant to say the t-distribution, but it's similar. It would be in the same ballpark. So having a test statistic that is 8 standard errors above the mean is crazy. So this p-value is going to be super tiny because this is so far into the right tail. We're going to have almost no p-value at all. In fact, it's probably going to round to 0. So let's figure out what it is. We're doing a right-tailed test, so the area will be all in one tail. Hang on, I gotta unprotect the sheet. Okay, so I had a protection on this sheet because I'm going to share it with you and I don't want you to accidentally mess up anything in the format. So I did protect it. If you need to unprotect it for any reason, the password is the word unlock, and that will unprotect it. So if you have any issues, you can do that, but I wouldn't recommend it unless you need to, because if you accidentally erase something, then what will you do? I guess you could download it again. Okay, so now we're about to do the p-value equals the area, so norm.distribution, the area to the right of my test statistic. So if I use this test statistic, it's going to give me an area to the left of the test statistic, and I want the area in my right tail, so I'll need to go ahead and subtract that from 1. So notice that it rounds to 0. It's what we call 0 plus in statistics because it's technically not 0. If you go out enough decimal places, it'll show you that it's not 0, but it's close enough to 0. So we're going to go ahead and just put 0 in here. And that means we are definitely going to reject the null hypothesis. This test statistic is so far out in the right tail that there's no way, or almost, I would say there's very little chance that this mean that was in the claim, 2.9, I think there's very little chance that the mean GPA of night students is 2.9, and it's definitely going to be significantly larger. All right, so that's how you do that test.